Hey everyone, I'm back. So I stopped the recording and I thought I was going to go to sleep, but then I took a look at the scoreboard and I realized that there were actually very few people who had solved D. And so I decided, okay, maybe I'm not being dumb. Maybe this is just a really hard problem. And so I decided I was going to keep debugging for a few more minutes, and I ended up fixing one bug and getting AC on the small set, and then another, and now I have AC on the full set for a AK on the round. So I figured I'd go ahead and record some explanations to my solutions real quick, and then I will. I'm probably not going to go into too much detail because it's nearly 2 a.m. my time, and I'm incredibly exhausted. I think I've been up for the last, I don't know, 18, 20 hours or so, and it is not pleasant. So, but I'll go through my solutions real quick. I'll try and talk through A through C in some detail, and then D, I'm just going to skim through my idea. All right, so problem A, we're given a 3x3 grid of integers with the middle square omitted. We can replace the middle square with whatever we want, and we want to ensure that that there are as many arithmetic progressions in the rows, columns, or diagonals as possible. Okay, so there's sort of two steps to the solution to this problem. So step one, figure out which arithmetic progressions exist regardless of g sub 1, 1. And what I mean by that is when we look at these grids, when we look at a grid, there will be some arithmetic progressions that don't include g sub 1, 1, and those will be in the grid no matter what we choose for g1, 1. And so an example of this would be in the top row. Let's see, what's an example that's in the sample test case? So like in the first sample test case, in the rightmost column, we have 11, 9, 7. That's an arithmetic progression, and it doesn't depend on 1, 1. So the first thing we do is we count those, and we can just look for all the ones that are possible, and it turns out that so this includes the top row, bottom row, left column, and right column. And so my loop over here checks those and it increments the answer because those are going to be part of the answers no matter what. So the next step is is to figure out the best value of g sub 1, 1. And so the idea here is the middle cell can be a part of up to 4 arithmetic regressions. It can be a part of both diagonals, and it can be a part of a middle row and the middle column. And so what I do is I maintain a map add, and for each, and the idea is that add of I stores the number of progressions containing g sub 1, 1 given that g sub 1, 1 equals I. And here there's 4 cases to include. There's this one is the main diagonal. This one is the anti-diagonal from 2, 0 to 0, 2. This one is the middle row, I believe, and this one is the middle column. Now the one thing that's left to discuss is to figure out whether something is an arithmetic progression, or alternatively to figure out whether or to figure out like what we need the middle term to be in order to make something an arithmetic progression. And the idea is this: if x, y, z is an arithmetic progression, then y minus x equals z minus y, or alternatively 2y equals x plus z. And so this is the equation I use for this first step where I'm checking if these arithmetic progressions already exist. And then here the idea is g sub 1, 1 is in the middle of all the progressions that can include it. And then we have y equals x plus z over 2. Okay. And so then what I do is I check whether these sums are even, and if they are, I add them to the answer, or I add them to the add array. And then I pick the best element of the add map, which represents the maximum number of progressions corresponding to any value of g1, 1, and I print that as the answer. Okay, that's problem A. So problem B. we're given n intervals, each of which can be is represented by 2 positive integers, and we can perform a maximum of c cuts, which cuts all intervals that contain that element, or the element x, not as an endpoint. And we want to find the maximum number of intervals that can be obtained. Okay, so the main idea here is, first of all, performing any one cut is not going to change which cuts are available to us in the future, except for the fact that it makes no sense to cut at any one point twice. And so what we need to do is essentially to figure out how many intervals will be cut if we cut at each position x, and then we can cut at whichever positions will go through the most intervals. And so what this basically reduces to is, given a set of intervals for each point, so given a set of intervals, find the sum. I guess a simpler or a one way to solve the problem would be to find the number of intervals covering each point, and at that point we can then say, or we can then take whichever points are covered by the most intervals and use those as our c cuts. And this is enough to pass the small test case, because with n equals 500 and the bounds up to 10 to the 4, we can easily just simulate we can easily just directly count the number of intervals containing each point, and then we can sort them and find the best cuts. However, this is insufficient to pass test set 2, because c can be up to 10 to the 18, and so simulating the cuts directly is going to be too inefficient. But what we can make use of is the fact that there are only n intervals, and so and if no interval starts or ends within a range, then that means that the number of intervals covering each point in that range will be the same. So we can sort of think about this by looking at the interval start and end points, and solving the problem on the ranges. Okay. So the way I implement this is I store this map events from a start or end point to the number of, or to the essentially the operations that are being performed at that point. And so the idea here is I'm saying, okay, the interval from the interval x to y can be cut at the points in the range, or in the interval from x plus 1 to y, including x plus 1 and excluding y. And that's because we can cut it at any point between x and y that's not x and y. And this just turns out to be a nice way to represent it in my code. In general, with a lot of these sorts of problems where you're compressing an array of intervals, it makes sense to sort of think in terms of half-open intervals just to make the code a little easier to write. And so the first step here is I iterate through the events, and then at each endpoint, I push CNT, which stores the number of intervals covering each point in our range, and then the current time minus the last time we've seen, which stores the length of time in there. And then I add the number of intervals we've added and delete the number of intervals we subtracted from the count. And so that gives me this queue where I've got sort of the number of, or where I've got pairs representing the where the first element represents the number of intervals covering a point, and the second element represents the number of points. And so while this queue is empty, I pull the top element and I figure out, okay, we'll remove, so we're going to process these such that we're taking the element or the intervals covered by, or the points covered by the most intervals first, and then we're going to either take all of these points if we can, or if C isn't large enough, we're just going to take the last C points. And then we subtract this value rem, the number of cuts we're making, from C, and we add rem times the number of intervals that we're creating to the answer. Okay, let's look at C. So we're given n sets of problems, each of which can be represented by a interval from a sub I to b sub I, and we have to test test m students. Each student has a skill level, and we want to find the problem closest to that skill level and then remove it to the set. So the main idea of this problem is we're going to maintain the set of we're going to maintain the set of intervals such that or I guess let me phrase it this way. Maintain the list of available problems as a set of intervals. So initially the set of intervals is just going to include a sub I up to b sub I. But then, like, let's say, for example, we have the interval 5 to 10, and then we take out problem 7. Then that becomes two intervals from 5 to 6 and from 8 to 10. And the reason that this works out pretty nicely is that removing a problem will break one interval into at most two intervals. And so what that means is we start with n intervals, and we add at most m intervals over the course of the process. And so at no point will there be more than n plus m intervals in our set. And so like there's a pretty feasible number of intervals to deal with. And so my solution essentially then becomes casework. So this first case, I use basically a pretty annoying set bash, but this first case occurs when our skill level x is contained within an interval. And if that's the case, then I just take the problem x itself. If not, then the second case occurs when the nearest point is the beginning of the next interval to the right, and this last case occurs when the nearest problem is the end of the next interval to the left. And so the rest of this is a set bash. I've got my code on screen. It's 2 a.m., so I'm not going to go over it line by line. But I'm happy to answer questions about the implementation in the comments. From here, though, this is it's a good idea to get familiar with problems like this because set bash problems of this kind are relatively common on a number of programming contest platforms. Okay, problem D. This one is very difficult, and I'm very tired, and I did not rigorously prove my solution. So I'm not going to explain it in full detail, but I can hopefully give you a general idea of my thought process. So we're given a prime number p, and we're given a function v that's the degree of p and the prime factorization of an input x. And so we want to process updates and then range queries where we print the sum of this formula over all elements in a range. Okay. So let's write a sub I as kp plus r. So that is r where r is equal to a sub I mod p. And so we're essentially splitting a sub I into the part that's divisible by r and the part that isn't. So then the formula becomes kp plus r to the s, or v of kp plus r to the s minus r to the s. Okay, so let's split into two cases. First, let's say r equals 0. Then v of kp to the s, or kp, this becomes v of just kp to the s. And we can show that this is equal to s times v of kp, which is equal to s times v of a sub I. And so this means that when a sub I is divisible by p, it contributes s times v of a sub I to our answer. And so I handled this case just with a seg tree. It's seg1 in my code, where if it's even, then this get value v essentially stores the number of times v is divisible by p. And so so it stores v of a sub I, and then in our answer I multiply it by s. Okay, so case 2, r is non-zero. So then the key idea is this. We can expand this polynomial using the binomial theorem, but it turns out, so the first term is kp to the s, and then we have a bunch of other terms, and then the second to last term is s kpr, and the last term is r to the s, but we subtract out r to the s, so that goes away. The key idea is that usually, our v is going to equal v of s kpr. And so in particular, we can show that that this is equal to v of s plus v of kpr, or I guess actually v of s plus v of kp plus v of r. And we know that v of r is 0 because r is not divisible by s. And so what that means in my code is I use seg3 to count the number of times v of s is included, and seg2 to count the value of kp, which is also v minus v mod p. And then I add that to our answer down here. And so we can show, the proof is kind of annoying to deal with, that this holds whenever p is greater than 2, s whenever s is odd, or a sub I is not equal to 3 mod 4. So there's kind of this one little edge case where p is 2, s is even, and a sub I is 3 mod 4. I do not know a rigorous way to handle this case, so I wrote a brute force program, and I just printed out a bunch of answers, and I was able to find a pattern where essentially in these cases we would have the same answer as before, except it would be increased by v of a sub I plus 1 v of a sub I plus 1 minus 1 and so I do not have a proof of this property. I basically wrote a brute force generator and then I made the observation. If anyone I'm guessing that a proof will be included in the editorial. If not, if anyone would like to attempt one, please feel free to post one in the comments. I might give it a try when I'm feeling more awake. But yeah, so that is so that's basically my solution. And so what I did is I wrote this update function that essentially updates the segment trees as I described above, and then the rest of the implementation is pretty simple once you do all the math. So the main hard part of the problem is deriving these properties, and in particular I spent over an hour handling this edge case. I think over an hour. I know it took a lot of time. Felt like a really long time. And then the other key idea to think or to understand is that in this term usually it's going to, or the v is just going to equal v of s kpr. And the reason for this, by the way, is that, or the intuitive explanation, this isn't a rigorous proof, is that typically, so like the term before this is s choose 2 kp squared. This actually should be r to the s minus 1. Kp squared r to the s minus 2. And because we have the p squared rather than the p, in most cases this thing is going to include at least one more copy of p than this thing. And the one case where that doesn't occur is when we have a denominator 2 in the s choose 2 thing. And so when we divide by when p is 2 but then we divide by 2, then this could actually like have the same power of p involved. But in general, for the most part, the v of all of these terms before is going to be greater than the v of this term, and so the v of this term will determine v of our overall function. So yeah, that was the contest. Let's see how we ranked. Alright, looks like I am currently in second, so yeah, definitely much better than I expected early on, but of course, it's a shame that, oh actually, okay, this guy finished way ahead of me, so there's not really much I could have done other than, take the round at a time that isn't in the middle of the night. But yeah, fun contest considering the hour. And I think that's about it. Please feel free to leave questions in the comments. I will answer them after I've gotten a good night's sleep. And thanks for watching.